All right, so here we have this is an induction question. Now, before we do this problem, I want to review something from the previous chapter, which is force on a wire in a magnetic field. So look, I'm going to just draw in this region of magnetic field, and then let's say we have a wire. So I'll put a circuit here coming up like this, and let's just add a resistor here like that. Now, the current in this circuit is going to be looping around like this. Now, what's the job of a magnetic field? What do magnetic fields do? Magnetic fields exert force on moving charged particles. So here we have a current, this current in the wire, like right here. Would the magnetic field exert force on this wire? Yeah, because if you think about it, what current is it's moving charged particles. In fact, in physics, we always define current as positive charge motion. So you can just imagine this stream of positive charges moving through this circuit like this. There's millions and millions of them. Okay? Now, the equation for force of a magnetic field is QVB sine theta, but something interesting happens to this question. If your moved charges are inside a wire, the QVB equation becomes something else, but it's really the same equation. So let's call the length of this segment of wire L. From there to there is going to be L. And so the equation for force magnetic, we're going to go Q. Now, what would the velocity of this particle be? The velocity of this particle in terms of L. What could we put in for velocity? What's the definition for velocity? Basically, length over time, right? If you take L, which is the distance from here to there, and divide by the time, that's velocity. Velocity would be L over T, and then there's B, and then there's sine theta. Now, what is Q over T? Q over T is current. So this is where we get this equation, which we're going to use this equation in this problem. We get this equation of F force magnetic. If it's current in a wire, Q over T is I. It becomes ILB sine theta. And if you remember back, you might be thinking, oh, we never did this, but I'm pretty sure we did, because remember I said the way when I first learned this, I remembered Bill, B-I-L. Right? Just rearrange this, force magnetic, because it wouldn't stick in my head, so I just remembered Bill. Force magnetic when it's on a wire, B-I-L. Okay, so now let's get to the problem. We're going to use that equation in a moment. Okay, so we have this bar sliding on these rails. We're given the magnetic field is 2 Tesla. We got a resistor over here that's 3 ohms. And we're given what the induced current is. We have an induced current of 2 amp, which tells us this bar must be moving. Because do you see a battery anywhere in this circuit? No. So the only explanation for having this current is it's not magic. It is not black magic. There is a induced voltage. An induced voltage is happening because the flux in this loop, so the loop is this area that I'm circling right here. We're focusing inside that area. Inside that area, there must be a change in magnetic flux. Whenever magnetic flux changes, you get an induced current. Now, there happens to be an equation that applies specifically to this. Induced voltage in a loop, when it's a bar moving through a magnetic field, the equation is BLV. Boom. Now, where does that equation come from? I want to show you. The master equation for induced voltages is N times change of flux over time. And that's where this equation comes from. I'll show you where it comes from. So N is the number of loops. How many loops do we have? 1. Now, in this problem here, what's changing the flux? Well, the flux equation, there's an equation for flux. B, A, cosine theta. So what is changing the flux here? Is the magnetic field changing? In this problem, is there a change in this magnetic field? No, magnetic field staying constant at 2 Tesla. Is there a change in the area? Yeah, because this bar is either moving to the right or moving to the left. And if the bar moves to the right or the left, it's going to change the area of the loop, right? The area of the loop. If the bar goes to the right, what happens to the area? It gets bigger. What if the bar goes to the left? The area gets smaller. So it's due to change of area. So let's, in this equation, what can we say for change of flux? Change of flux is going to be B times change in A over T. Oh, and the cosine theta here, in this situation, the theta is 0. There is no change of theta. Theta is the angle between the normal line to the loop and the magnetic field, which in this case is 0. Has everybody got that? I've showed you that a bunch. So we can just set this to 1. Cosine of 0 is 1. Now, next thing. What can we say about the change in area? Well, let's say the bar is moving to the right. Let's say it moves a distance d to the right. What would the change of area be then? If it moves a distance d to the right, the change in area is going to be this region, the change in area, not the final area. So it'd be d times L, right? So we're going to say B. The change in area here is going to be d times L over T. But wait a minute. What's d over T? D over T is what? V, which is where we get this BLV equation, like that. Okay, where V would be the velocity of the bar, how fast the bar moves. And by the way, does the bar have to be on rails? Does the bar need to be on rails to get a potential difference across it? No. Yeah, so what completes the circuit? Then you get a current running through it. But even if you just had this bar moving through a magnetic field, you'd still get a potential difference across it. Okay, so now let's solve the question. The first question is determine what speed the bar must be moving. So the velocity of the bar is going to be the induced voltage divided by BL. Okay, now what's the induced voltage? Oh my gosh, it's 6 because we can figure it out. We have 2 amps across 3 ohms. Everything else is assumed to have 0 resistance. So just do Ohm's law. You do E equals IR. So the induced voltage, we have 2 amps across 3 ohms like that. Or I should say going 2 amps through 3 ohms gives us 6 volts. So we know that the induced voltage must be 6 volts. And then the magnetic field is constant at 2 Tesla. And then the length of the bar is 2 meters. So then this comes out as 1.5 meter per second. Boom. Okay, now, which way is the bar moving? Is the bar going to be moving to the right or to the left? So this is Lenz's law. Let me just explain step by step. So the induced current is going counterclockwise, which means, so I'm going to write this out, which means inside this loop, the induced current makes a B field that is which way?
What do you mean? Oh, it makes it out of the page.
That is out of the page. Okay, this is the first thing you must realize. The induced current makes a B field that's out of the page. And how did I do that? Right hand rule number 2. That's how I figured it out. So if you loop your 4 fingers, go like right here. Loop your 4 fingers around there. The magnetic field from the induced current. Dudes, look at. Am I talking about this magnetic field here? No, I'm not talking about that magnetic field. There's a second magnetic field here, which is the magnetic field created by the induced current. So the induced current is making a magnetic field that is directed out of the page. So what does Lenz's law say? Lenz's law says that the B field, it says that the change in flux, the change in magnetic flux must be opposite the field created. Maybe this wasn't a good idea to write this out. Lenz's law says that the change in flux must be opposite the field created by the induced current. So, if the induced current makes a magnetic field that is out of the page, which way must the change of flux be? Into the page. So what's going to give a change of flux into the page? The bar moving to the right or the bar moving to the left?
To the right.
To the right, and here's why. If you think about it, here, let me revert this. If you think about this, if the bar moves to the right, what's happening is this area here is opening up. The area is opening up. Is that going to let more magnetic field in or less magnetic field? More. That's going to let more magnetic field in, as opposed to if the bar was sliding to the left, that's going to be closing this area, which is going to let less magnetic field in. That would be a change to out of the page. So we want a change that's into the page, which means the bar must be sliding to the right. That way our change of flux will be into the page. Okay? All right, boy, we're still on part A. Okay, part B. Determine the magnitude and direction of the external force that must be applied to the bar to keep it moving at this velocity. Now, watch. This goes back to the original thing I was talking about, which is if you have a current in a magnetic field. Remember over here, this is how we started. We had a current. I set up a little battery like this. So whenever you have current in a magnetic field, the magnetic field is going to exert a force on that wire. Now, if the current is running this way, just watch. If the current in this bar is running up the page like that, which way is the force of the magnetic field? So we got to use right-hand rule number 1 here. Right-hand rule number 1, you go like this. It's the flat-hand rule. So the current is going up the page, positive charge motion. Magnetic field is going in. So which way is the palm of my hand facing? To the left. Right-hand rule number 1, and this is from chapter 19. This is from magnetic fields. The force of the magnetic field is going to be to the left on that bar. If the current is running up, positive charge motion, it's like this. Stick your thumb in the direction of the current. Magnetic field's going in, into the page. The palm of my hand is to the left, right? Which means the force magnetic is to the left. But wait a minute, which way did we say the bar was moving?
To the right.
The bar was moving to the right, so there must be some applied force here. I'll call that FAPP for applied force, or let's just call it FA for applied force. Okay? So like this. So what we've established is this. So we erase this. I need to put it in my diagram. So what we're saying is the force of the magnetic field is to the left. There must be an applied force to the right. And what the question wants us to find, determine the magnitude of the external force that must be applied to the bar to keep it moving at this velocity. They are talking about this force right here. They're talking about this applied force. So how the heck can we get that applied force? Well, if you think about it, if this bar, if you sum the forces in the x direction, we have force applied to the right, force magnetic to the left. The sum of the forces always equals ma. Well, hold on. Is this bar accelerating? No, because it's moving at a constant velocity. It's moving at a constant velocity. So therefore, the applied force equals force magnetic. Oh, wait a minute. Do we have equation for force magnetic on a current in a magnetic field? Yeah, we do I, L, B, sine theta. But sine theta here is going to be, that's going to be 90. The angle between the magnetic field and the motion of the charged particles is 90. That's just 1. So the force applied, we're just going to go ILB. So it's going to be 2 amps times 2 meters times 2 Tesla, which gives 8 newtons. Like that. That's part B. Okay, we're halfway done. Okay, part C. Hey, will you get the door? It's going to get loud here. Thanks. Okay, part C is really wordy, but it's really not that hard. What are they talking about here? In part C, it says determine the rate at which heat is being produced in the resistor. What the rate at which heat is being produced in the resistor. What are they really asking for? Power. Because rate of heat, look at the word rate. The word rate is anything per second. Rate means per second. Heat is energy. We're talking about energy per second, energy over time, so which is power. So we have to bust out the what? The power equations for circuitry. So here are the power equations. So first of all, the basic definition of power, you could say power is work over time. You could say that power is energy over time. So this is where we get joules per second, right? Energy is also joules per second. What do we call joules per second? That's called a watt. But hold on. Are there power equations a little more specific to what we're doing? Yeah. So you could do P equals I times voltage. You could do P equals I squared R. Or you could do P equals delta V squared over R. Basically, here's how I taught this to you. If you know this first equation, you can get the other two equations by substituting in Ohm's law. Delta V equals IR. Just plug that in there, and you get the remaining two. Now, which power equation is going to be the nicest one to figure out the power of this resistor? I would just use I squared R. I'd go I squared R. 2 amps, right? Because we know the current flowing through it. So 2 amps squared times 3 ohms. This comes out as 12 watts. Oh, and just be aware on the solutions that I gave you. I didn't type them up. I'm going to pass it. I'm going to pass the blame. Whoever typed up the solutions put 12 ohm as the answer. That's a typo. It should be 12 watt. Okay, so we got 12 watt for the resistor.
Is there solutions?
Huh?
Did you put the solutions on window?
Yeah, I'm going to post all the solutions.
Hey, he's filming right now.
Hold on, I'm recording. Let's talk business later. Okay. Okay, now, determine the mechanical power being supplied to the bar. Let me show you how to do this. So power, one definition of power is work over time, but hold it. What's the definition of work? Force times distance. Well, what's distance over time? Velocity. So a nice way to get the power delivered to this bar, because there's a force pulling this bar, the applied force, which is working against the force of the magnetic field. So if we take the applied force pulling on this bar multiplied by the velocity of the bar, which we have, then we get the power. And watch what happens here. So what was the applied force? 8 newtons. What's the velocity? 1.5 meter per second. Notice this comes out as 12. Is that a coincidence that it came out the same?
Yeah.
No, it's not. Because the idea is the energy being supplied to the bar by this applied force, where is it coming out? It's got to go somewhere. It's coming out over here in the form of heat out of the resistor. Okay? Now, final question, and this one's quick. Suppose the external force is suddenly removed. We take this applied force away. Let me revert back. So we've established that we have this applied force to the right. We have this applied force to the right, and we have a force magnetic to the left. What's going to happen if we remove this applied force? If this applied force disappears, is the bar going to continue moving? No. It's going to slide. Well, it won't start moving to the left. It's going to slide and then come to rest some distance later, right?
Isn't there a magnetic force applying it?
Yeah, well, the force of the magnetic field is going to be to the left, but the only reason we have a force magnetic is because we're changing the flux, right? The only reason we have this is because we have this induced current. Without the induced current, there is no force magnetic. So once the applied force is removed, the bar is going to stop. So the question says, suppose the external force is removed, determine the energy dissipated in the resistor before the bar comes to rest. Where's the energy popping out of this resistor? Ultimately, where is it coming from? The motion of the bar. What type of energy does the bar have before the applied force is removed? It has kinetic. What is the initial kinetic of that bar before the applied force is removed? Well, 1/2 mv squared. So the kinetic initial is going to be 1/2. The mass of the bar is given right here, 4 kilograms, and then the velocity was found to be 1.5, like that. So this gives us a kinetic initial of, what is that? Oh, I didn't calculate this. What is this? 1.5 squared, basically times 2, 4.5 joules. So how much kinetic is it going to end with after it slides to a stop? 0. So how much energy is going to pop out of this resistor? The answer is 4.5 joules.